Hello everyone, this is Dr. Lennon, and we are going to go over the Module 1 homework. I'll probably make this into 2 videos since the first module is pretty long. It's 64 questions. It's a lot of review from pre-algebra, so let's jump right in. We're going to go over most of the problems, and on your homework they should be similar but with different numbers. So on this first one, we've basically just got a plug in and evaluate problem. So we've got 3x minus y for x equal to 10 and y equal to 6. So basically what we're doing is we're just changing the x to 10 and the y to 6, and then we need to remember to evaluate according to order of operations. So the method for evaluating order of operations, remember, is PEMDAS, where really there's only 4 sets of operations, because multiplication, division, and addition, subtraction we do as they appear from left to right. So again, I'll just remind you this stands for parentheses, exponents, multiplication, division, addition, and subtraction. And addition and subtraction are the same operation. Multiplication and division are the same. You just need to do them as they appear from left to right. One is not granted precedence over the other. So here we start with the multiplication. 3 times 10 gives us 30, minus 6, and then we have our answer is 24. So we can enter that here, hit enter, and we are all set. So again, we've got another order of operations type of problem. For number 2, we've got some exponents in, and they want us to plug in x equals 9. So for number 2 here, we have, let's see, 8 plus 8 times the quantity x minus 8 to the 3rd power for x equals 9. So we're just going to plug in 9 where the x is. So we have 9 minus 8 inside the parentheses. So from order of operations, that is the thing we will do first, which is pretty straightforward. 9 minus 8 is 1. Now we will evaluate the exponent. So 1 to the 3rd power is just 1. So we have 8 plus 8 times 1, which is just 8 plus 8, which adds up to 16. So we're all set on number 2. Okay, so for the third one, we get into some intersection. So if you have 2 sets as we do here, we have 2 kind of operations for combining sets. This symbol means intersect, and these are, what this means is elements common to both sets. And you also have the other operator, the upside down that looks like a U. This one is the union operator, and these are elements in either set. So in one set or the other or both. So in some sense, intersecting 2 sets is going to make it smaller. Performing the union of 2 sets is going to make that a larger set. So when we look at number 3 here, we have these 2 sets, which are essentially just lists of numbers, 1, 6, 7, 8. That set is being intersected with 6, 7, and 10. So to find the intersection, we just look at the elements that are in both sets. So we see 6 and 7 are in both sets. So those are the common elements. So when you intersect them, you just have 6 and 7, and that's it. So we would select A here and do 6, 7. And then for number 4, we have a union. We already discussed. We're taking all elements in one set or the other or both. So when we perform that union, what are we going to have? Again, if you never list the elements twice, you just list them once. So if something does appear to be in both, like 14, we're not going to write it twice. So what is the union? This is going to make them a single set. We have 5, we have 8, we have 13, we have 14, and we have 15. So it's all the elements in one set or the other, or both. And we are all set. Okay, so this next one, we're talking about important sets of numbers that we encounter frequently. So let's kind of talk about what those are first. So for number 5 here, we have, let's work from the smallest sets of numbers to the largest sets. So the natural numbers, these are also known as the counting numbers. This is just the set of the numbers you would count. 1, 2, 3, and so on, all the way up to infinity. You can just count up forever. So all your positive whole numbers. Now, if we say whole numbers, we're just throwing in one more number. The only difference between whole numbers and natural numbers is we are going to include 0. So the whole numbers start at 0, not at 1. And they keep going as such. Then we have the integers. The integers are slightly larger. These include 0, the counting numbers, and also the negative numbers. So it goes in both directions. So we could say, okay, -3, -2, -1, 0, 1, 2, 3, and we continue in both directions. So we've got all the positive, negative, and 0 whole numbers. The rational numbers is where they start to get a bit bigger. So the rational numbers, there's 2 ways to think about them. You can think about them as any number that can be written as a fraction. So you can think of them as all things of the form a over b, such that a and b are integers, and b is not equal to 0. Cannot divide by 0, so we need to include that as well. So that's one way to talk about the rational numbers. In high school, another common way is you can talk about them in their decimal expansion. So this is the set of all decimals that terminate or repeat. So that's another way to think about your rational numbers. What's an example of a decimal that repeats? Well, 0.33333 repeating forever. That's one such example. And we all recognize that as the fraction 1/3. Okay, and then the irrational numbers. Probably the easiest way to think about these is in terms of that decimal notion. So these are decimals that neither terminate nor repeat. So decimals that neither terminate nor repeat. So some examples of those. A lot of times they're represented by numbers, so or by letters, Greek letters. So square root of 2 is one such. If you plug that into your calculator, you get an infinite decimal expansion that doesn't ever have a pattern. We also have numbers like pi or e. These are some of these famous constants. A lot of these famous constants are often irrational numbers. Technically, the square root of any prime number is going to be an irrational number. Okay, and then real numbers. These are kind of basically all the numbers we typically encounter in this class are going to be real numbers. There are imaginary numbers that deal with I, the square root of -1, but real numbers we could think of as any number on the number line. So any number that can be found on the number line. It's probably the easiest way to think about it. So all of these groups of numbers that we've talked about so far, they all are contained in the real numbers. Okay, so let's go ahead and look at this. Basically, we want to pull these numbers and see what groups they belong to. So if they're in the group, we want to pull them in there. So 0, we know that's a whole number. That's an integer. It's a rational number. You could think of it as a fraction, like 0 over 1. It's not going to be an irrational number, though, because that does terminate. And it will be a real number. Okay, so we've got 0 done. How about 0.25? Where does that go? Well, it's not going to be a natural number, a whole number, or an integer because it's a fraction. And the decimal does terminate, so that makes it a rational number and also a real number. Notice the rational numbers and the irrational numbers are mutually exclusive, meaning if a number goes into one of those groups, it will not go in the other group. So if something goes in the rational bin, it will not go in the irrational bin, and vice versa. Okay, how about the square root of 100? Well, the square root of 100 we know is just the number 10. So that's the better way to think about this. Where would 10 go? Well, 10 is a counting number, which also makes it a whole number, which also makes it an integer. 10 also has a decimal expansion that stops, and it will be a real number. Again, all of these will be real numbers. Square root of 5, that's the square root of a prime. It's kind of like the square root of 2. So that will be an irrational number, and it won't go anywhere else except for the real numbers. We have the same thing with pi. We know pi is irrational, so that goes here, and it also goes into the real number bin because all of the numbers will go in there. Okay, negative 2/7. Well, that's not going into any of the groups in the top row, but it is a fraction, so it'll be rational. So we can pull it into the rationals and also into the reals. I don't know if did it go in there? Oh, it's getting a little tricky. All right. Okay, and then negative 14. Negative 14 is not natural or whole because it's negative, but it is an integer. It will also be a rational, and it will be a real. And then we have classified them all. So that's it for number 5. Kind of a long question, but you just have to understand what the groups are. Okay, so number 6 here is absolute value. So remember the absolute value of a number. So one way we could define the absolute value of, say, x is it's going to be two things. It's going to be either x if x is greater than or equal to 0, or the opposite of x if x is less than 0, right? The absolute value always gives the distance from 0, and distances should always be positive. So for instance, if you did the absolute value of 8, you would just get 8. If you did, say, the absolute value of negative, let's say 4, we would just get positive 4. So the question is, they want us to rewrite this absolute value of 16 minus pi without the absolute value parts. So basically, it's either going to be 16 minus pi, or it's going to be the opposite of whatever that number is. So you just have to ask yourself, is 16 minus pi a positive number? Well, pi is about 3.14, so it's already positive, which means the absolute value doesn't do anything here. It's just going to be exactly 16 minus pi. Now, you don't want to actually type 16 minus 3.14 into your calculator because that is an approximation. Pi really has an infinite decimal expansion, so we're just going to leave that symbol as is. So we're just going to type 16 minus pi here, and that is the result. The absolute value bars are just kind of superfluous there. Okay, so let's look at number 7 here, another one with some absolute values. So number 7, we have negative 3 over the absolute value of negative 3. And similar to order of operations, we want to treat the absolute value like parentheses. So we want to perform that first. So the absolute value of the negative 3 in the denominator will just turn out to be positive 3. And then negative 3 divided by 3 comes out to negative 1. So we have an answer of negative 1 for number 7 right here. Okay, so express the distance between the numbers using absolute value. So we can write that down maybe as like a proposition. The distance between two numbers A and B is given by the absolute value of B minus A. You just subtract them in their absolute values. So in this example, so our question here is how do we find the distance between -1 and 8? Well, we can do it just using the theorem above. So we have the absolute value of 8 minus -1. And that's going to be the same as the absolute value of 8 plus 1, which comes out to be the absolute value of 9, which we know is just 9. So they're 9 units apart. For the first thing, they do not want us to simplify, so we're going to write it like we did in the very first step, 8 minus -1 in the absolute value. And then we know when we simplified that, the answer was 9. So pretty straightforward there. Okay, number 9 is very similar, so we'll skip over that one. Same exact process here. And yeah. Okay, so there's a bunch of properties. It might be useful to just look these up when you're encountering them. I'm not going to make you memorize them all. There's quite a few. Generally, commutativity means flipping the order, and associativity means looking at different parenthesization of the same expression. So clearly, this property that we're looking at only involves addition. So you could pretty much rule out everything on the right-hand side. Those all say multiplication, and we can actually rule out the bottom one on the left-hand side. So we'd just be looking at the first 4. Identity property of addition would be adding 0. A plus 0 is A. Commutative property of addition just says A plus B is the same as B plus A. Inverse property of addition would say A minus A is 0. Associative is what we're looking at here, which tells us if we use parentheses in a different manner where everything is added, we're still going to have the same result. So this is associativity of addition. And then this one right here, this is maybe worth writing down. This is the distributive law. So number 11, we have the distributive law, which tells us how addition and multiplication interact. So this is the one we'll encounter most frequently. So if we have some A times B plus C, the way we can remove the parentheses, if we have some variables involved, right? If everything was a regular number, we could just combine inside the parentheses first. But if not, then we need to go about it in a different way. This is actually A times B plus A times C. And you'll see that's what we are doing above. If you have 8 times -6 plus 4, this would be the same as 8 times -6, which is minus 48, plus 8 times 4, which is 32. So that is the distributive property of multiplication over addition. Okay, so number 12, again, we're utilizing the distributive law to do a little bit of simplification. So for number 12 here, we have 2 times the quantity 5x minus 7 plus 13x. So we start by distributing. 2 times 5x will make 10x. 2 times -7 will be minus 14. And then we have plus 13x. Now, when we're adding terms that contain a variable, we can only add them if they have the same variable expression attached to the number. So in this case, 10x and 13x are said to be like terms. We can combine them. And they are combined by just adding the coefficients, which are the number in front of the x. So we know 10 plus 13 makes 23. So that tells us essentially that we have 23x, and then the minus 14 stays on its own. It does not have an x with it, so it is not a like term. And that's the full simplification of this algebraic expression. So we're just left with the 23x minus the 14. And number 13 is going to be very similar. We may have a bit more simplification to do, but we distribute twice here and then just again simplify by trying to find the like terms and add them together. So we have 7 times a 2y minus 6 plus a 3 times a 5y plus 4. So we start by distributing the 7. 7 times 2y is 14y, and 7 times minus 6 is minus 42. Then we distribute the 3 to the second set of parentheses. 3 times 5y is 15y, and 3 times 4 is plus 12. So we have two sets of like terms, the 14y and the 15y. So 14 plus 15 is 29y. And then we also have minus 42 and 12, the regular numbers. They don't have any variables with them. So negative 42 plus 12 comes out to negative 30. So that's our fully simplified algebraic expression, 29y minus 30. Okay, let's do number 14 as well. It looks pretty similar, but I do want to point out one thing that's just a touch different. It almost doesn't look like we're distributing anything to the second set of parentheses, but when we do have a minus sign, we have to treat that like a regular number as well. So, although it doesn't have a number in front of the second set of parentheses, it is subtracting the second set of parentheses. So we need to distribute the negative sign to both terms, both the 3y and the 2. You can also think of it as adding negative 1 times that set of parentheses. That's an equivalent way to formulate it. So start by multiplying the 7 through the first set. We have 49y minus 42. And distribute your negative sign. So we'll have a minus 3y, and then we'll also have a minus 2. Okay, so let's collect our y terms. 49y minus 3y makes 46y. And minus 42 minus 2 will make minus 44. So we have 46y minus 44. Okay, number 15, we have some nested parentheses, meaning a set of, we see the round parentheses inside the square brackets. What you do is you just work on the innermost set of parentheses, simplify there, and then work your way outward. So we're going to start with the 6y minus 2. So there's a negative sign to distribute, and we'll start there. So for number 15, we have 6 minus 7 times 3 minus the quantity 6y minus 2. So distribute the negative sign to the 6y minus 2. So we have 6 minus 7, square bracket, 3 minus 6y, and then minus negative 2 becomes plus 2. So inside that square brackets, we can add the 3 and the 2 because they're regular terms. So we'll be left with 6 minus 7, square bracket, 5 minus 6y. Okay. Now we need to distribute that minus 7 across the square brackets to remove them. So we have 6 minus 35, and then minus 7 times minus 6y is going to be plus 42y. Keep ending up with plus 42y in all of these examples. Okay, then what are our like terms? A 6 minus 35. So 6 minus 35 is negative 29 plus 42y. So you could write it as 42 minus 29 or negative 29 plus 42y. It doesn't really matter. I'm just going to enter it as we did it here. Typically with polynomials, you will write the highest powers of the variable first, but we'll look into that a bit later. Okay, so we've got some rules of exponents coming up. Any number raised to the 0 power is going to come out to be 1. So that's one of the rules of exponents. Let's see if we follow up with some more interesting ones. Okay, so evaluating some of these, let's maybe look at some rules of exponents as they appear. So one of them, if you have a to the 0 power, this is equal to 1, where a is not equal to 0. 0 to the 0 power is an indeterminate form, so that would not evaluate to 1 necessarily. The second one we have, if we have a to the negative n, this is the same thing as 1 divided by a to the n. So in the example above that we have we have 3 to the negative 5. So to evaluate that, that has nothing to do with the sign of the number, but instead it's saying this is the same as 1 divided by 3 to the 5th. And we know that 3 to the 5th, what is that going to be? That's going to be 243. So this should be 1 divided by 243. Notice the number itself is actually a positive number, even though we started with a negative exponent. That negative exponent really means like divide by 3 5 times. It doesn't have anything to do with a negative sign. If you take a positive number to any exponent, it's still going to be a positive number. So here we're going to write 1 divided by 243. Okay, we're encountering another law of exponents here. So we're just kind of going through them case by case. So if we have a to the m raised to the nth power, in this case we would multiply those two exponents. So we would have a to the m times n. So our for example is going to be this problem. 4 to the 4th raised to the 3rd power. This would be the same as 4 to the 12th. And if we want to evaluate that, oh gosh, that's going to be a big problem, a big number. Maybe we'll use the calculator here. 4 to the 12th. Yeah, quite a large number. 16,777,216. Okay. All right. Back to a bit of a simpler problem. Okay, so, gosh, I got rid of that, didn't I? What was it? 16, some big number. I forgot to write it down on the sheet here. 4 to the 12th. Yeah, 16,777,216. Okay, that was quite a large number. For number 4, the property that we're seeing here is if you have, so there's kind of two properties that go hand in hand. I'll list the one that doesn't apply first. If you have a to the m times a to the n, the same base being multiplied, then what happens here is you actually add the exponents. So I don't know, let's say we had I don't know, 2 squared times 2 to the 3rd. This would be 2 to the 2 plus 3, which is 2 to the 5th, which would come out to 32. If instead you are dividing, what happens is you subtract the exponents. So a to the m over a to the m would be a to the m minus n. So that's what's going on here. We have 7 to the 5th over 7 to the 3rd, which would be 7 to the 5 minus 3, or 7 squared, which comes out to 49. So we're subtracting the exponents there. 5 minus 3 makes 2. Okay. Again, this x to the 7th times x to the 7th, we'd be using property 4. The base is x, and we just want to add those two exponents. 7 plus 7 would make 14. So this should be x to the 14th. So we've kind of got a recap of exponents. What are we doing here? This is property number 3, which says that we want to multiply those exponents. If you look back at property number 3, we have x to the 11th to the 8th. So we would, 11 is acting like m, and 8 is acting like n. So this should be x to the 88th, just applying property number 3. Again, we've got the same thing here for number 22. We're multiplying the exponents. So 9 times negative 3 is negative 27. But notice the instructions say to write your answer using positive exponents. So we know this is x to the negative 27th, but that's a negative exponent. So from property number 2, we can rewrite this as 1 divided by x to the 27th. And notice the exponent's positive now, since we've written it in that fraction form. So that's what they mean when they say write with only positive exponents. If I try x to the negative 27th, it should mark it wrong. So you notice it says incorrect. But if I now write it in the form that they asked, 1 divided by x to the 27th, it should give it to me. Yep, and there we see it. Okay, let's look at number 23 here. Some more exponent issues. So the trick to evaluating this one is you need to apply that exponent to each part. So this is going to be, you have to square the 8 and you also have to square the y to the 4th. You have to square both parts. So 8 squared is 64, and then the second part, y to the 4th squared, that's property number 3 from the exponent rules we did above where we multiply. So 4 times 2 makes this y to the 8th. So this is going to be 64 times y to the 8th. There we have it. Okay, so something similar here for number 24. We need to apply that exponent of 3 to all the relevant parts inside the parentheses. So you may think of it as 3 parts. Well, we have the negative in front, so you could think of that as -1. So we have -1 to the 3rd. We have the 3 on top of the fraction, so you could do 3 to the 3rd. And then we also have the x on the bottom of the fraction. So we have x to the 3rd. And then just simplify all the parts. -1 to the 3rd is -1. 3 to the 3rd is 27. So we have a -27. And then x to the 3rd is already simplified. So this simplifies to just -27 over x to the 3rd. So you've got 3 different components there. And we just raise all of them to the 3rd power. And then simplify. And that's how we get our answer. Okay, same thing here. We have 3 different parts, and we want to raise all of them to the 4th power. So for number 25, we have -3x squared y cubed raised to the 4th. So let's do each part. So I have -3 that I want to raise to the 4th power. I have x squared that I want to raise to the 4th power. And I have y cubed that I want to raise to the 4th power. -3 to the 4th power, that's going to come out to +81. So you can use your calculator if you're not so good at doing those in your head. And then for the remaining 2, we're using that third property I listed above, where we just multiply the exponents. So 2 times 4 makes 8, so we have x to the 8th. And 3 times 4 makes 12, so we have y to the 12th. So our simplified expression is 81 x to the 8th, y to the 12th. Okay, number 26. What's going on here? Well, we've got 3x to the 8th times 5x squared. Now, there's nothing really to distribute with the parentheses, so really the best thing to do is just group the 2 things that you can kind of combine. So we know we're going to do 3 times 5, and then we also know we want to do x to the 8th times x squared. The regular numbers can be multiplied normally, so 3 times 5 would make 15 as usual. And then remember, this is property number 4 from the exponent rules we listed. Since they both have the same base of x, the final 2 factors, you want to add those 2 exponents. So 8 plus 2 would make 10. So this is 15x to the 10th power. We're adding up the number of factors of x that appear. So we have 15x to the 10th. And then we've got something similar going on here with 27. So for number 27, we have minus 9x squared y times minus 4x to the 9th y to the 6th. So again, let's start. Basically, we're going to have 3 groups of things. We're going to have our regular numbers, our x's that we're going to group together, and then our y's. So let's just kind of rewrite the order here. We've got -9 times -4. We've got x squared times x to the 9th, and then we'll list our y's. Y times y to the 6th. So -9 times -4 is just positive 36. Nothing too fancy there. And then again, you add the exponents for the bases that match. So the x's match, so 2 plus 9 makes that 11, so I get x to the 11th. And now I need to combine y and y to the 6th. Now notice if you just have y, there's not a power written there. So if there's not a power written, that power is implicitly 1. We typically just don't write it. So really this should be y to the 1st times y to the 6th. So 1 plus 6 will make 7. So it will be y to the 7th. So our final answer there is 36, x to the 11th, y to the 7th. Okay, let's continue. Number 28. Now instead of multiplying the letters and numbers, we've got some division going on. Remember, that's all that means for the exponents is we're going to be subtracting them rather than adding them. So we have minus 4, x to the 4th, y to the 7th, over 2x squared, y to the 4th. So negative 4 divided by 2 is negative 2. And then we just want to subtract. 4 minus 2 gives me x squared, and 7 minus 4 gives me y to the 3rd. So I've got negative 2 x squared y to the 3rd. We didn't have any negative exponents here, so there wasn't anything tricky. If we did, we'd have to rewrite them as we did with one of those previous problems. Whenever we have fractions, a lot of times they're going to have some positive exponent rules, as we see here. So for number 29, we have 7x to the 7th raised to the negative 2. So again, we want to do each part to the negative 2. So we have 7 raised to the negative 2, and also our x to the 7th we want to raise to the negative 2nd. So again, that's going to be 1 over 7 squared for the regular number. And then we multiply the exponents as per rule number 2 above. So 7 times negative 2 is negative 14. So we have x to the negative 14. 7 squared is 49. And we only want positive exponents. So this is going to be 1 over 49 times 1 over x to the 14th. Or we could write that as a single fraction, 1 over 49, x to the 14th. So that's what we'll have here. All right, number 30, we've got some more exponent simplification. Again, this is just rehashing your skills with rules of exponents. So we have 30 x squared y squared over 18 x to the 4th y to the negative 3rd. Okay, so 30 over 18, those are both divisible by 6. So if you reduce that fraction 30 over 18, that's going to be the same thing as 5 over 3. So we can simplify the regular numbers into a fraction in lowest terms, 5 over 3. Now let's deal with the other two variables. So again, we want to subtract the exponents top from bottom. So we have x to the 2 minus 4, and then we have y to the 2 minus negative 3. So if we simplify a bit, we have 5/3 x to the negative 2, y to the positive 5, right? Subtracting negative 3 is the same as adding 3. So 2 plus 3 gives us y to the 5th. Now they want us to only use positive exponents. So that means this x to the negative 2 is going to go to the bottom and become a positive exponent. So we're going to be left with 5 y to the 5th on top, and then on bottom we'll have 3 times x squared, making sure that that exponent is positive. And that's going to be our final answer here. So 5y to the 5th over 3x squared. Okay. So probably just 2 more problems and we'll end this video and then finish the rest of Module 1 in Part 2. Would put us exactly at the halfway point. So for number 31, we have 3x to the 8th over y. All of this is raised to the negative 2. Again, I think about this as 3 factors. your 3, your x to the 8th, and your y, and we want to raise each of those to the negative second power. So we have 3 to the negative second, x to the 8 raised to the negative second, and then on the bottom we're going to have y to the negative second. So let's try and simplify all of these parts. 3 to the negative second is, well, that's going to go to the denominator for now. So we'll have x to the negative 16th. 3 squared would be 9, but it's a negative, so that's going to put it in the denominator. So we're going to have 9 there, and then y to the negative second. Now they want all of these to only have positive exponents, so that means if you put it in the other part of the fraction, it will just switch the sign on the exponent. So that means essentially the 9 is in the right place, but y to the negative second is going to come to the top and now become a positive 2 rather than a negative, and the negative 16, well, that x will go to the bottom and then become a positive 16 rather than a negative 16. That's property number 2 we had for the rules of exponents. So this is just going to be y squared divided by 9x to the 16th. Okay, and this is talking a bit about scientific notation, which probably we'll continue with next time, but for now, notice that it's pretty straightforward. If you have 2.3 times 10 to the 5th, this just means what we want to do if we want to write this in decimal notation without this times 10 to the 5th, it's moving the decimal 5 places to the right. So we could take this 2.3 and move this decimal 1 spot, 2, 3, 4, 5, and for all the spots where there's nothing there, we would fill it in with zeros. So this would come out to 230,000. So that would be the answer. If you would multiply by 10 raised to a negative exponent, we would just move the decimal to the left rather than to the right. That's pretty much all you need to understand to change scientific notation back to standard decimal notation. Okay, so that's it. We will stop here. So this will be part 1 of the Module 1 homework, and we will continue in the next video with the second half. So this is Dr. Lennon signing off.